Hi, for the lecture today we are going to talk about high order derivatives. We have learned how to differentiate a function, and now we take a derivative of a function and differentiate it again. So first we are going to justify and motivate why would we go ahead and repeatedly differentiate the same function. So I'm going to talk about velocity and acceleration. Then we are going to talk about graphical interpretation. We are going to look at the pictures of all of these functions all at the same time and try to see what's their connection. Next, we are going to learn how to write higher order derivatives and the notation for them. Next, we are going to have a quick introduction to Factorial to use it for the higher order derivatives of some basic famous functions, among them 1 over x, x to some power, and some simple trig functions. At the end, we are going to go ahead and talk about implicit higher order differentiation. Okay, to motivate the topic, let's go back to something we have seen several times. Suppose s is a function of time, so t represents time and s represents position. So a particle could be moving or an object could be falling, and we are recording its position at a certain time. What is velocity? Velocity, we have learned, that is derivative of position with respect to time, or to show it by s prime. So this is the velocity. Velocity itself is some function of time. As time changes, typically velocity of whatever particle it is you're looking at could change. So this velocity is a function of time. Sometimes you are interested in how fast the velocity is changing. Well, that is represented by acceleration. Acceleration is the derivative of velocity with respect to time, or you could show it as v prime. And acceleration itself could be a function of time, and you might be interested in studying all of these at the same time. Sometimes people go ahead and even study rate of change of acceleration. So that shows up in your text as j, and that's the rate of change of acceleration with respect to time, and that again could be a function of time, and that is referred to as jerk, an appropriate name here in this context. Okay, so jerk is the rate of change of acceleration. So we have a sequence of derivatives we are taking. We are starting with the function, differentiating it, get another one, differentiate that one again, and get a third one, and differentiate that one again, get a fourth one, and so on. In many dynamics problem that you are going to study later on, you just deal with the position, velocity, and acceleration. This repeated differentiation shows up in some engineering examples, like studying the deflection of a beam or something like that, and there you might even have higher order derivatives. Most of the physical laws, however, they go 2 differentiations deep. However, in mathematics, we are going to have uses for very high order derivatives. That's going to be a topic you're going to deal with in Calculus 2, but now we are just laying the foundation by taking a look at the first few derivatives. Okay, let's go ahead and briefly talk about the graphical connection of all of these derivatives. Let me go ahead and draw a function that you have seen in some of your older exercises. Here is my coordinate system. I'm going to take this to be time, and then go ahead and record the location of an object as a function of time on this curve. So here is some curve. So let's call it S. S is a function of time. So one item we are showing in this axis is S. What do we mean here? What we really mean is that we have perhaps a real number line or an axis, or if you wish, we have a particle on a road. So let's draw a highway or a road here, and suppose you have some origin on that road. So here is our axis or the road. For sake of clarity of our discussion, let me just give some numbers for this special location here. Suppose this is time t equal to 1 second, and say this is say 3 seconds, and say this is 5 seconds. What do we understand from this picture? We understand that, well, some places it's negative, some places it's positive, and then again S is negative, and again it is positive. What does that imply about the position of the actual particle? Well, when S is negative, it means we are on the left of the axis. When S is positive from 1 to 3 seconds, it means we are on the right. At 3 seconds, we are crossing the origin again. And then when it is negative, when S is negative, it means we are on the left. At 5 seconds, we are crossing the origin, and then we are going to the right. So the actual movement of this object is perhaps something like this. It's coming from the left. Well, how do I know I'm coming from the left? Because S is negative here. I'm coming from the left. When time is 1 second, I'm crossing the origin. So I keep traveling along, and then sometime I decide to come back. So I'm coming back. Now imagine this whole thing is happening on this road, but just to show the movement, I have to move it off of itself. So I'm coming back. At what time do I cross the origin again? At 3 seconds, I'm crossing here again, and then I'm moving to the left. At some point, I stop and turn around, come back toward the origin. So again, I'm turning around. Once again, I remind you the whole thing, the zigzag movement is occurring on just a single line. So at 5 seconds, I'm crossing the origin again, and I'm on the right, and I keep going. So there is a zigzag happening like that. This is the position itself. Now, how would the velocity look like? Velocity is the derivative of the position. So derivative of position here is a very high derivative. That means we have a high velocity. A velocity drops because the slope is dropping. At this point, velocity becomes 0. So my velocity is high and positive. I'm coming down. After this, velocity is negative. It's like putting on the brake. Velocity is negative means we are turning back, turning left. The velocity stays negative all the way up to here. So at this point, velocity is 0 because I have a horizontal tangent line. These are the points at which velocity becomes 0. So I'm turning around somewhere. The graph of velocity is turning around, and then after this, velocity becomes positive again. If velocity is becoming positive, its graph is going to be above the axis. So it's going to look something like this. So this is the graph of the velocity. Again, for the sake of convenience, let me choose some round numbers here. Suppose this is 2 seconds and say this is 4 seconds. What do these times 2 and 4 refer to? At time 2, we are turning around. We are coming back toward the origin. Up to this point, velocity was positive. After that, its velocity is negative. At that point, its velocity is 0. So time equal to 2 seconds is this location. At that time, we turned around. Time t equal to 4 seconds. Okay, so between 2 and 4, velocity is negative. That means I'm going left. Time t equal to 4 seconds, I'm turning around again. And then come back and go to the right side and pick up speed. Now, one could go ahead and differentiate velocity also and get the acceleration. So I could have acceleration of this. Here, acceleration is negative because I'm differentiating v, and this at this location the slope is negative. So acceleration is going to start negative, and at some point it's going to turn to 0. Here accidentally it's just at the same point 3, and turned out to be positive afterwards. So the acceleration could look something like this. So this is acceleration as a function of time. Here acceleration is negative. That means velocity is dropping, and this particle, if to make a simple example, if it were a car, perhaps you're putting on a brake. After this point, acceleration becomes positive, and after 3 seconds it is somewhat similar to putting on the gas. Now, the comparison to movement of a car is not very instructive here, because on a car you have a back gear and a forward gear, and description of those here is going to make the issue more complicated. So oftentimes we are going to talk about the particle that is moving around. It could be moving around because of gravitation, or it could be moving around because of electrical field and such. But one thing that you need to learn is to see the graph of a function, its derivative, and the derivative of a derivative, and try to connect these items to each other and see how you can label one of them as the original function, and label another one as its derivative, and label the third one as a derivative of the second one, and so on. We are going to have several examples like this in the exercises, and I hope you do a few of them. Okay, the next item that we are going to take a look at is the notation that we are going to have. Let me go up here and describe the notation here. So for the issue of the notation, we said S is the initial position, V is the velocity. We are taking velocity and differentiating it again. So I might go ahead and rewrite it in this style. I say V itself was S prime, and then you are differentiating it one more time, so it's going to be prime on top of another prime. We are going to do away with these parentheses and just write it as a double prime here. So taking S and differentiating it twice is going to be written as S double prime. If I wanted to do it here, well, I have to take A and differentiating it one more time. So that's going to be S double prime, has to be differentiated that third time, and we abbreviate the whole thing and write it in this notation with triple primes. As I mentioned, in a physical application, essentially one or two differentiation is all that you do. But in mathematics, we plan on differentiating a lot more. And this notation is going to look rather awkward if you want to put, say, 10 tick marks on top of a name. We have to have alternate notation. So let's go ahead and talk about notation here. So suppose I have y as some function of x. Let's throw away the concepts of application to physics and just take a generic function. Y is equal to f of x. For y prime, we had several notation. These were the two that we are going to emphasize a lot more. Okay, if I take this function and differentiate it one more time, I'll have y double prime. What if I want to use this Leibniz notation? In that case, I'll have the derivative of then that function that I already developed here, d dx of f. Well, d is going to be written with the exponent of 2, and denominator, this dx is one single item, and that is squared as well. It's written as d2 dx2 of f. That's the Leibniz notation. Here is the third one, triple prime of y. We have to take a derivative of this one more round, and the way we are going to write it is d3 dx3 of f, and so on. Now in this notation, if we want to go beyond 3, we can use Roman numerals, or sometimes we just start writing numbers. Now if I just write 4, the danger is that it's going to be confused with the power of 4. To make sure that we can convey to a reader that I intend to differentiate 4 times, they use the number of differentiation, put it in a parentheses to indicate that that's what they really want to do. So in this prime notation, that is going to be written in this style. And of course, if you wanted to use some other notation, you could do, sometimes you might see notation like this as well, but we prefer these numerical notations and insist on using them. So our favorite notation past 3 is going to be either this style or this style. Okay, that is for the notation. Next, we want to go ahead and just practice some simple examples. Suppose I have f of x is equal to x squared plus, say, x cosine of x. What is f prime? I have to differentiate this as usual, 2x. Differentiate this one, derivative of first times second is cosine of x, derivative of second times first minus x sine of x. If I want to differentiate twice, derivative of this will be 2, derivative of cosine of x minus sine of x. Derivative of that one, I have to apply the product rule. I'll have another minus sine of x. Derivative of x is 1 times sine. It's going to be minus sine of x. Derivative of sine is cosine, and that's going to make me minus x cosine of x. Perhaps sometimes some simplification might be in order, so I'll have 2 minus 2 sine of x minus x cosine of x. If I have to differentiate a third round, derivative of 2 will be 0. Derivative of minus 2 sine of x is going to be minus 2 cosine of x. And here is an issue that comes up repeatedly in these problems. That if you have done something such as differentiating x cosine of x, keep an eye on that, and if it shows up again, just use what you have already developed as opposed to reinventing the whole thing. So in this case, be aware that there is a minus sign in front of it, so I write minus of whatever I had here, or if it's comfortable for you, you might as well just go ahead and differentiate one more round. But keeping this in view is going to help you with some of the problems that you're going to encounter. So in this problem, it looks like I am coming down to minus 3 cosine of x plus x sine of x, and so on it goes. Okay, let's take another example. Suppose I tell you that f of x is x to the power of 10. F prime of x going to be 10x9. F double prime of x, well, I'm applying the power rule. Triple prime of x would be 10 times 9 times 8 x to the power of 7, and so on. You see this peculiar coefficient that starts to develop here, product of consecutive numbers. That's a very common theme that comes up in this repeated differentiation. So for that reason and many other occasions in mathematics, we need a notation that we are going to be using, and that's a notation of a factorial. Factorial, well, most of you are familiar with the notation. If I have a number with exclamation mark in front of it, that's going to be read as, for example, in this case, 5 factorial. And by that we mean the product of all the numbers starting from 1 to that number. So far we are assuming that this is a positive integer. So I have to multiply all these numbers, and in this case it's easy to verify that you get 120. What if I wanted to calculate 6 factorial? Well, 6 factorial, it's whatever I had here that has to be multiplied by 6. So it's really 5 factorial times another number which is 6. So I just multiply that one by 6 and I get 720. Of course I could develop it from scratch. I could have written it 1, 2, 3, 4, 5, and 6. But it's good to pay attention to the properties of the factorial. One of them is that each factorial is the number itself times the product of the previous times the factorial of the previous number. So here we have this notation. If n is a number such as 2, 3, 4, and so on, then n factorial means 1 times 2 times 3 times as many of them it takes until you arrive at the n itself. Now in many cases it's going to be necessary for us to define 0 factorial as well. We will see shortly why that is needed. But 0 factorial essentially implies a multiplication that can't be done because you can't start from 1 and reach 0. In all such cases, multiplication over an empty set is defined to be as 1. So without further ado, we are going to just define 0 factorial as 1, and just pay attention that 1 factorial is also 1. 1 factorial, you're just starting at 1 and there is no multiplication to be done. So 1 factorial is just 1. It's good to go ahead and write the first few factorials. 2 factorial, 1 times 2. 3 factorials, 1 times 2 times 3, that's 6. 4 factorial is 6 times 4, that will be 24. 5 factorial we just did. 6 factorial was 720, and so on. This is a sequence of numbers that you better have it in the back of your mind. You are going to encounter that very often, and any time that you come across this particular sequence, you better remember n factorial. Okay, let's put what we have learned to good use and differentiate a particular function. Suppose I ask you find 25th derivative of f of x is equal to 1 over x. So I'm starting with the function 1 over x. To differentiate this, might be easier if we write this in the negative exponent, x to the power of minus 1. So when I want to differentiate that, just say exponent up front, and the exponent has to be lowered. Now you can always go back to the ordinary notation and write this as minus 1 over x squared. Let's go ahead and take the second derivative. Well, now I have to multiply this new exponent with this one, so I'll have minus 1 times minus 2 x to the power of minus 3, which you can simplify as 1 times 2 over x cubed. Let's try one more round. Triple prime is going to be minus 1, minus 2, minus 3, x to the power of minus 4. That is 1, 2, 3 over x to the power of 4. Except now I have an odd number of negatives, so the negative survives in this case. Fourth derivative, we said we are going to write it in this style, or here's another. We are going to have one extra number up front, minus 2, minus 3, minus 4, x to the power of minus 5, and minuses cancel. I have 1, 2, 3, 4 over x to the power of 5, and so on. Notice that if I had multiplied these numbers, I would have lost the flavor or the pattern that is developing here. Sometimes it is better not to do too much arithmetic so that you see the pattern. Once you multiply the numbers, it's rather hard to see where they are coming from. So to state this thing again, this is really minus 1 factorial over x squared. This is 2 factorial over x squared. This is minus 3 factorial over x to, excuse me, here was cubed. And here is 4 factorial over x to the power of 5. Now, if we see the pattern, we can guess what's going to happen if we continue these things 25 times. If I arrive at 25th derivative, so that is 25th derivative of y, what do you think we are going to have on the right hand side? It's probably a good place to pause and give your answer and come back. Several things we need to guess. Is there a negative sign up front or not? What factorial is going to be sitting in the numerator, and what power is going to be sitting in the denominator? Looking at the pattern that is developing, when I have an odd number here, I have a negative here. Two derivatives. Let me write this in the other notation. It's y1 really. This is y2. This is y3. And so on. So when this number is odd, meaning 1, 3, 5, and so on, I have the negative up front. So I write that. This is 25, so I will surely have a negative. Next, number in the numerator is the factorial of how many times you are differentiating. So if you want to differentiate 25 times, this is going to be 25 factorial. 25 factorial is a huge number. It's best left in that format. You might try it on your calculator to see it's really a huge number. X to the power of what number is going to be the exponent here? So always one more than how many derivatives you have taken. So this is going to be x to the power of 26. As a good exercise getting you ready for next semester, you might want to try to come up with a formula. What if I wanted to do this thing? I forgot to write y here, sorry. the nth derivative of y. In this case, well, some portions of it is easy. Numerator is just n factorial. Denominator is going to be x to power of 1 more than n that you have. And here we have a sticky issue. It's what is it that's the sign in front of this? So is it going to be positive or negative? What kind of a formula can you develop that's going to do the job for you automatically? So let me just write something that will hold the place for it. What would be a good letter for this? Well, it is a sign, so I might put a S here. What is S? S is going to be a positive sign if n is even. S is going to be a negative sign if n is odd. If the number of differentiation is even, you put a plus. If the number is odd, you're going to put minus. Well, that's a bit unsatisfactory to have a verbal expression for some function. Let's see if we can come up with something a little bit better than that. Well, in this case, it's rather easy. If you take if you want to find out the formula for S, you can take -1 and raise it to power of n. That will do the job. If n is even, it's going to make it positive, and if n is odd, it's going to make it negative. This is really nothing other than what we had here. If I hadn't erased these negatives, I would have had that available to me already. I had, in the case of the third derivative, I had 3 negatives to multiply. So if I had written it as minus power of 3, that would have automatically told me this is going to be a negative number. And here I had 4 negatives. So let's make it a positive number. So with that in mind, I can go ahead and write my formula in the following way. dn or dxn instead of y, let me write down what function it was, so we drop as many unnecessary items as possible, is equal to -1 raised to power of n times n factorial over x to power of n plus 1. So here is one formula we derived here. Other than that variable x, we have some order of differentiation, which shows up on the right hand side in terms of some factorials and also some powers. This is a kind of situation you are going to see very often in Cal 2. Those of you interested, I'll recommend that you try to do the following. Try to find out the nth derivative of, say, 1 over x to power of 5 or some power. See what happens. Or try to find nth derivative of. These problems gradually become more and more challenging, but they are good exercises in seeing the patterns and tracing them, tracking them, trying to simplify things, and so on. These are all good exercises. So here what the exponent was 5. Okay, let's go and take a look at some functions that are more immediate for our uses. Sine and cosine. Suppose my function, so here's we are starting another example. Suppose y is, let's say, sine of x. We are going to go ahead and differentiate this thing several times. First derivative, of course, is cosine. Next derivative of cosine is minus sine. Third derivative of minus sine is minus cosine. And the fourth derivative of minus cosine. Cosine itself gives you a negative. Another negative makes it positive, so we are going to recover sine. what do you think is the next one? The fifth derivative of this is going to be, of course, cosine. What is happening here? I'm sure you noticed by now that the pattern got repeated. So here I had sine, cosine, minus cosine. Now it's happening like that again. Sine, cosine, and if I want to go 2 more rounds, y6 is going to be minus sine, and y7 is going to be minus cosine. So if you want to keep track of things, well, this is y prime, you want to call it y1, this y2, y3. We might as well always use this parenthesis notation. And for the sake of uniformity, the very first function, the one you haven't touched yet, we might call it y0. You have taken 0 derivatives out of it, which means you haven't done anything yet. So for the sake of having an exponent over all of them, we went ahead and created that notation now. 0 on the top means just don't touch the function, leave it alone. So this is the pattern we see after every 4 we are starting all over again. Suppose I ask you the question, find 363rd derivative of this function, just for the sake of exercise. Well, of course, we don't want to go through this 363 times to see what we are going to land on. If we have a cyclic pattern, we are going to make use of that. So we notice that every 4 we are going to start the game again. So y8, of course, we are back to the sine. So that gives us an idea. Take this number, see how many cycles of 4 are going to be in it. So take 363 divided by 4, and of course you are going to get 90 complete cycles. We are going to go through 90 of these, and we are going to be left with 3. So after that, that's going to 0, 1, 2, 3. That's going to bring us to minus cosine of x. So the final answer becomes minus cosine of x. To write it again, if I start with sine of x and differentiate that, (363 times), I'll end up with minus cosine of x. So in all these cyclic phenomena, we divide by the length of the cycle. Length of the cycle is how many times it takes before you repeat yourself. Find out what is the remainder. We start with that and can't use that as our exponent. And that's going to give us the function that we want. I'll recommend that you go ahead and do the same thing for cosine. So here is a question. Find (51st) derivative of cosine of x. Sine and cosine are the only 2 functions that play this nice. If you start with any other ones, tangent and so on, all hell breaks loose, and the patterns are substantially more complicated. Nothing to do with what we are experiencing right now. They don't look like sine and cosine. Substantially more difficult problems show up over there. Okay. One last item that we are going to take a look at today, which is implicit differentiation of higher order. here let me pick a question. Suppose you have okay, sorry for the interruption. We are going to look at implicit differentiation of higher order, and we have let's take an example here. I take say x to power of 5 plus y to power of 5 is equal to say 1, and the question is find y double prime by implicit differentiation. Okay, what we need to do is first we need to find y prime itself. How do we do that? We go ahead, take this equation and differentiate it. So derivative of x to power of 5 will be 5x to power of 4. Maybe you want to stop this and go ahead, do this and come back. Derivative of y to power of 5 is going to be what? 5 y4 y prime, and derivative of 1 is 0. You remember our objective is to find this y prime. It's being a simple problem, we just move items without the y prime to the other side. So I'll have 5 y4 y prime. The right hand side I'll have minus 5x to power of 4. So from here I can find y prime, and that is going to be ratio of right hand side 5x4 over 5y4, and here is our answer. Y prime is equal to minus x to power of 4 over y to power of 4. Okay, that was just y prime. What we really need here is a y double prime. So next, more challenging one is to find y double prime. To find y double prime, I really need to go ahead and differentiate the right hand side of this. So just like minus x to power of 4 over y to power of 4, and then take a prime of that. We could go ahead and apply quotient rule. With all these powers, it is somewhat preferential if you use the power rule. So either way would be fine. Let me just, to keep the material a bit shorter here, x4 y to power of minus 4, and I want to differentiate that. Could put the minus inside or outside, that would be fine. With the power rule, I'll have minus derivative of the first is going to be 4x3 times the second. Derivative of the second is going to be minus 4y. Exponent has to be reduced. Be careful about that. It has to go down to minus 5, then times the first. That is going to be x to power of 4. So this derivative so far is let's take the minus or let's take as much as we can actually out of this. So I keep the minus outside. 4, I have 4 here and 4 here. I might take both of them out. X cubed, that is the factor that excuse me, I made a mistake here. Let me correct my mistake. Of course, when we differentiated y to power of minus 4 was minus 4y to power of minus 5, and here I made a mistake that I always tell you not to make. So y prime is needed by the chain rule. Going back here, minus 4x cubed. From the power of y, I have to pick the smallest exponent. Smallest exponent is, of course, minus 5. From here, I have y left. How is that? Minus 4 is the original exponent. Minus 5. That's going to give me y. And then from the second portion, I have taken y to power of minus 5 out. From x to power of 4 I have taken x cubed out. So I'm left with x and a y prime. Maybe you want to try this thing again with just a quotient rule, see if that is any easier to apply. Now, moving on, I have minus 4x cubed y to power of minus 5. What is left is that this y prime has to be written in terms of what we found here. So I'm going to write that instead of this y prime minus x4 over y4. So I'll write here y minus x, the y prime was minus x4 over y4. Was that right? x4 over y4. So we just copied that through. Let's go ahead and simplify a little bit more. Minus 4x cubed y to power of minus 5. I take a common denominator here, y to power of 4. I have to multiply this by y to power of 4. That makes it y to power of 5. Minus times minus makes plus, and x times x to power of 4 makes x to power of 5. One more round. This minus 4x cubed, let me write this in the denominator, y to power of 5. x5 plus y5. Better pay attention to the very first statement of the problem. x5 plus y to power of 5 was said to be 1. Notice that if we forget to simplify, our answer looks quite different. So here I have 1 over y to power of 4. Simplifying this one more round, I have minus 4x cubed over y to power of 9. So here's our final answer. Y double prime turned out to be minus 4x cubed over y to power of 9. Rather interesting relationship. So that's the second derivative. About 2 years from now, you'll have the topic of differential equation, which is infinitely more interesting than what we have done. And the question there would be, starting from this observation or this equation, y double prime is equal to minus 4x cubed over y9. Can you find your way all the way back to where it came from? That is a lot harder and a lot more interesting than what we are doing right now. At any rate, you go ahead and do the exercises of this section. We have covered quite a bit of ideas, simple ideas. Each of them need at least a couple of exercises, and I hope you do them. Good luck and